In this video, we're going to talk about trigonometric integrals. So this first slide is just a couple of remembering of some trig identities that are going to be important in doing trigonometric integrals and doing trigonometric substitution, which will be the next video. So these first three here are just your Pythagorean identities. So you've got your sine squared x plus cosine squared x equals 1, your 1 plus tangent squared x equals secant squared x, and your 1 plus cotangent squared x equals cosecant squared x. A couple of other ones that pop up in these are your what are typically referred to as the half angle formulas or the power reducing formulas. Sine squared can be written as 1 minus cosine at 2x over 2, so this is why it's half angle. Notice that the argument in the cosine is double the argument in the sine. And then cosine squared x is 1 plus cosine 2x over 2. Okay. Alright, so let's talk about these trig integrals. Now, one of the reasons why I put those Pythagorean identities in there is because really all we're really trying to do in these trigonometric integrals is to rewrite the integrand into a form that we can see what the u substitution has to be. So in this first example, we've got sine to the fourth x plus cosine to the fifth x dx is what we're trying to integrate. Now, there are two logical choices for what to let u equal if you're going to try to make this a u substitution. They would be u equals sine x and u equals cosine x. Those would be the two logical choices for what to let u equal if you were trying to do this integral by a u substitution. Okay. All right, what would go wrong if you would try to let u equal cosine x? Think about what would go wrong with this one. Well, if I let u equal cosine x here, then my du would have to be negative sine x dx. So I would have to peel one of these signs off over here to make a du piece. That would leave me with sine cubed. We cannot easily change sine cubed into powers of cosine. Notice if I go back to the previous slide, we've got sine squared plus cosine squared equals 1. I can do even powers of sine or cosine and convert it to the other one easily, but not odd powers. Okay? So odd powers aren't helpful. So if I pull off one power of sine for du, I would have sine cubed, not an easy thing to change. Let's do it the other way. If we're going to let u equal sine x, we would pull off one copy of cosine for du. Now I've got an even power of cosine. That's a good thing, because I can convert even powers of cosine to powers of sine pretty quickly. I'll write cosine to the fourth as cosine squared squared, and then we can change cosine squared to 1 minus sine squared. So now we can do our u substitution fairly quickly. Let u equal sine, our du is cosine. Here's du. I can put a u in here. I can put a u in here. All references to x go away. So I get u to the fourth times 1 minus u squared squared du. I can FOIL out the 1 minus u squared squared piece and distribute the u to the fourth through. Now I've just got a polynomial to integrate. That's easy to integrate. And then at the final step here, put back in what u is equal to. Okay. So again here, we're motivated by basically what the du piece has to be and how to change the one function that we're given, one trig function we're given in terms of the other. All right, let's look at this one. Secant to the 7th x, tangent to the 7th x dx. Pardon me. All right, so again, let's think about what would happen if you try to make a u substitution. Two obvious choices, u equals secant or u equals tangent. Those are your two obvious choices. If we were to choose u is equal to tangent x, du would have to be secant squared x dx. You would have to pull off two pieces of secant. That would leave me with a secant to the fifth. That's an odd power. That's hard to change. Okay? So let's go the other way around. We're going to let u equal secant. Then du is secant x times tangent x. That leaves me with, this is going to be our du, so we're not going to mess with this one anymore. That leaves us with the 6th power of tangent, which again, easy to change that over with even powers. That's tangent squared cubed. I can change tangent squared to secant squared x minus 1. And now I can do my u substitution. Because my u is going to be secant, my du is secant tangent. So we get u to the 6th, u squared minus 1 cubed. It should be a du there, not a dx. Expand, right? We need to cube that binomial and multiply the u to the 6th through. But no big deal, maybe a little bit of algebra big deal, but no big deal as far as integral goes because this is a polynomial. Anti-differentiate that fairly straightforwardly, and then substitute in what u is equal to. Let's do another one. This one, notice, is we're not going to be able to do the same thing like we did in the first example because we had, in this case, we don't have an odd power of sine or cosine. So we'll have to use that power reducing formulas to help us get those down to odd powers. So let's do that. First, let's convert everything into sines. Let's get that done first if we can. Cosine squared, just to make things a lot simpler for us. Cosine to the 4th is cosine squared squared. Now let's use our power reducing formulas for both of those. Multiply everything out and simplify. I can pull the 1/8 out in front. If you distribute everything out, this is what you should get when you multiply everything out. This is going to be the one that's tricky again. We can handle odd powers pretty quickly. It's the even powers that we have to redo. So let's use our power reducing formula on that one to get cosine squared down to a cosine to the 1st. Notice when we went from cosine squared x to 1 plus cosine 2x over 2, that had to double the argument. We double the argument here as well. So the 2x becomes 4x when we plug it into the formula. Here, we're setting up for a u substitution, so I can pull out a cosine 2x for du, and then I'll have a cosine squared 2x is what I need to substitute back in for. All right, simplifying some things. Just breaking up the minus sign here. 1 minus a half gives you a half. Then I've got a 1/2 cosine 4x here, and it'll be a minus because that minus out in front. This last integral piece here is a u substitution. Here I'm just, again, simplifying some things. So here, when you distribute the cosine 2x through, you get a minus cosine 2x, a plus cosine 2x. Those go away, so it makes it a little bit simpler. Now we're ready to anti-differentiate. These pieces are relatively straightforward. Antiderivative of a half is a half x. Antiderivative for cosine 4x, I would get a sine 4x, but I need to adjust with a 1/4 for that 4 that's in there. That's where the 1/8 comes from. Same idea here. If you do a u substitution here, I need to adjust for a half for the 2, and then a 1/3 will because we're integrating the u squared. So that's why it's a 1/6. The half is coming from the 2 to adjust for that, and the 1/3 comes from integrating squareds to cubes. You should go through that u substitution, make sure you understand how to get bound. And then here we're just distributing the 1/8 through. All right, so that was an example of kind of the harder idea when you have even powers of sines and cosines together. You have to use the power reducing formula and just keep working your way down until you get everything as far as odd powers go. We can also get difficult ones that pop up with secants and tangents. So first, let's just look at it for an antiderivative for secant. So here, to get this antiderivative, we'll do a little bit of a quote-unquote trick. We'll multiply by 1 cleverly. Multiply top and bottom by secant x plus tangent x. Distribute your secant x through the top. And now notice if I let u equal the denominator, the numerator is the derivative. U equals secant x plus tangent x. du is secant x tangent x plus secant squared x dx, which is exactly what I have. So the u substitution here gives us du over u, which I know how to anti-differentiate here. So here we get an antiderivative for secant x is natural log of the absolute value of secant x plus tangent x plus c. Rather than having to go through this every time if you come across the antiderivative for secant and need it, I would suggest just memorizing this particular formula. It's just easier than trying to reproduce this little quote-unquote trick every time you have to integrate secant of x. It's just simpler to, if you can memorize the trick, you can memorize the formula. Alright, so let's do an odd power of secant here. Let's do secant cubed. Alright, so let's first rewrite secant cubed as secant x times secant squared x. Rewriting it as a product because now I can do an integration by parts with the product. I can differentiate the secant and I can anti-differentiate the secant squared. Those are formulas that we know. Applying the integration by parts formula, we get secant tangent minus the integral of secant x times tangent squared x, because when you multiply those two together, you get tangent squared. Tangent squared is something that we can substitute in a formula for. I can replace that with secant squared x minus 1. And then distribute my secant x through. Alright, so now we can break the integral up over the difference, and I know now the antiderivative for secant x. That was what was on the previous slide. So we get minus and minus is a plus there, so that's where the plus natural log of absolute value of secant x plus tangent x is coming from. But I still have this minus secant cubed x hanging out here. So going from where we started to where we are now, I've got this equation on the last line. Notice that it has secant cubed x on both sides. So I can move the secant cubed x over to the left-hand side. I now have two of them. The plus c comes from the fact that these really are potentially two different antiderivatives. So when I move this to the other side, it leaves a footprint, if you will. It leaves a plus c on that side because those two might differ by a constant. But now to finish this off, we divide both sides by 2 to get an integral of secant cubed x is 1/2 secant squared, 1/2 secant x tangent x plus 1/2 natural log of secant x plus tangent x plus c. So this one is more complicated to do, obviously. And anytime you come up with odd powers of secant, they tend to be more difficult to anti-differentiate. So there are some formulas that will pop up that you can use to help you work through it more quickly without having to go through all of this work by hand from scratch, if you will. So this is one of those that the secant cubed is probably one of those integrals that pops up enough that I wouldn't necessarily say memorize it, but have it somewhere close by that if you need it, you can just look at what the antiderivative is rather than having to rederive it like we did here.